Right, welcome back to another session on the Stack language. And today we are going to continue the self-hosting part of the language. And what does self-hosting mean is we have a compiler written in C, for example, in our case, and we built a language with really small set of features right now. And we are trying to use those sets of features to re-implement the language in itself, right? So currently the programming language that we implemented is powerful enough to um, you know implement rule 110, which means that the language is Turing complete, right? And that's quite good because it means we can do anything in this language, including implementing the language in itself, right? So that's already a good start. So last time we did a couple of experiments in trying to figure out how to approach this problem because yeah, it's I haven't done this before, so it's could be complicated. Not sure what the perfect solution is, right? So that's something we have to figure out together. But how I decided to approach this problem is trying to generate the assembly as soon as possible so we get something executable really fast. And that means we are going to try and skip. First, we are going to skip the tokenizer, the parser, the type checker, like everything, and we are going to start straight from the assembly. So we are just going to print out assembly with an executable that works perfect. Then we go one step back and add, for example, parsing. So we still skip the tokenizer, but we just parse tokens. Like we are gonna have an array of tokens and we are gonna parse them. And once we are happy with that too, we are gonna implement a tokenizer and we are actually gonna read files and do the entire process. So I think actually starting from the end of the compiler might be easier. So yeah, that's how we are gonna approach this problem. And last time we did quite a few things. If you haven't watched that video, I mean, it's a good idea to like get an idea of how it all started from the beginning of that. But in between that part and this one, I did quite a few changes. So I've changed some functions, especially the ones for pointers, right? Because I wasn't really happy with the memory management that we had. So I guess I should say memory layout. So I changed a few functions and yeah, I mean, it's not that big of a change. It's just that I wanted to have the capability of doing referencing and dereferencing because we didn't have that before, and it was kind of painful to work without it. And I mean, this kind of makes type checking harder because you can just do reference, and you wouldn't be able to tell because we don't have generic types, we don't have any of that. We just generate a pointer. We don't know what the pointer is. It's just a pointer, right? So that could be difficult for type checking, but we'll see in the future. Maybe in the future we'll have generic types. Who knows? But yeah. Anyway, let's skip that part. So the standard library is still exactly the same. We haven't changed anything except of these pointer functions, right? So now I had to update almost all of the code, like the implementation for memcopy, for example. And as you might guess, if we have memcopy, then we can really easily implement strings, arrays, and all of that stuff. So that's nice. But yeah, and the other change that since last time I'm like, whoa, the data types are again looking really algorithmic. So if you remember, I wanted to have data types in this language. So data types would be some kind of syntactic sugar for allocating a pointer and then initializing each field. So they're exactly like structures in C, right? They make your life a bit easier. You don't have to work with void pointers. You just use structures. So that's kind of what structures are gonna be in this language as well. And you can see that initializing looks kind of algorithmic in a way. So first we allocate some memory, then we do some, like it looks really bad, but if you look at it, it looks like a pattern emerges from initializing the fields. So I'm pretty sure we can at some point put this entire code back into the compiler, right? And even getting the fields looks a bit algorithmic, so it's always the same code. So that's kind of interesting, right? And yeah, so yeah, I mean, basically the language just has these data types, which are just wrappers around some pointers. It has functions and it has constants. And I mean, I went into a lot more detail in the first like 2 weeks because that's when we implemented each one. So, you know, if you want, I think the titles of the videos are pretty clear in which video each one happened. So I really recommend to watch those because you will really understand what these are about. But even if you don't understand yet, it's still fine. I mean, you probably get the point. Like these are just functions; they do some stuff. These are the inputs, these are the outputs, right? So you can see that it kind of does type checking. So that's already a good point for a language, type checking. So yeah, now I guess we can just start on working with the compiler. So let's I mean, you know, ideally in the ideal world, we would delete this main.c file and yeah, basically the code would be just the stack language. So let's get right into the stuff. Right, so as I said, I started with the AST. All right, so we have all of these data types that we also had in the C code. So these we wrote last time, but we haven't gotten yet into writing the init functions and the getters and all of that stuff. But if we go to our, I'd like to go to the AST, right? So the AST would be prog. So we have this structure, right? And I tried to basically copy paste the same logic. So in here we have the AST for a program. Right now it's gonna be just functions. We'll add more stuff later on, but right now we have only functions, right? Okay. Then functions in the C compiler, they are this kind of structure, stack AST func, and we also have that structure in stack as well, right? The name and the list of expressions, and then we have an expression but, and this is the part that I thought is gonna be interesting for today. In stack we have multiple kinds of expressions. We have conditionals, we have numbers, boolean, strings, function calls. So there are quite a lot of expression kinds, and right now I only added the number expression, and you might see a bit of a problem here. Stack doesn't really have enums, and here we kind of used enums. So yeah, like the problem would be how can we simulate, like we don't have enums, we don't have unions. So that's gonna be the problem that we are gonna try to answer for today. Like how can we have multiple options for the stack AST expression? So yeah, that's what we are gonna try to answer. But let's first take another look at the main function, right? So as I said, we are gonna start with an AST. So you can see that we build the AST here manually. Like we just literally initialize the data structure with some stuff, right? And then we just print the assembly. So I just copy pasted the entire assembly from the main.c file. Right, so we have some assembly here as well. Assembler emit, we emit the allocator, we emit the entry point, keywords, program, and constants. So I just copied all of them, right? And just put them in the compiler code. I put them at the bottom because I don't want to see them that much. Yeah, so it's just gonna print all of that, right? And again, currently, since we only have functions in our program, I'm just hard coding functions, right? And then for the functions, I'm just hard coding expressions, or I guess for functions you only have expressions, so that's fine, right? We print a function, and for the function we print list of expressions. For each expression we print one expression, and the expression currently is just a number. We don't have any optimizations yet, but hopefully we'll do. But yeah, like this is the current problem. We only have numbers, and I'd like to add function calls on my like on a video, because it's gonna be interesting to see that going, and then we'll see what else we're gonna do. But right now, if we run make, we build the compiler using C, as you can see here, right? We GCC, or I guess Clang. Then we have this main file, right? Which if we run help, we can see this is the stacklang compiler. Right? We can do stuff like running other programs, right? So in examples, you saw that we can compile this thing, generate the assembly, and we can also just take a look at what happens if we do that. So it generates some assembly. But what if we run our compiler on the stack.sl file, so on the newly built compiler, let's say. So we run that executable on this stack.sl file. So we generate some assembly. All right, it's a bunch of assembly actually. I'm actually curious how big it is. So let's put it into example.asm. Right, and let's open that example.asm file. So it's 8,000 lines of code, and all of this code is just what you just saw, right? Compiled using the C compiler. So next up, we just use FASM to compile the assembly into object, like .o files. Then we can use the LD program to link the O file into an executable, and we just built an executable. And the question is, what does this executable do? So let's try to run it. It just prints some assembly. Okay, so that's interesting. It just prints some assembly, and you can see here at the bottom there is this interesting function, right? So that function is somehow related to this AST here, right? So that's pretty cool. It's exactly that, right? It's just the number 69. So that's kind of interesting. So what would happen if we put this assembly into an assembly file, then we run FASM on that assembly file, then we link that object file into an executable, and then we run the executable? So what would happen is we get the answer 69. So we were actually able to just use the executable generated from this stack.sl file to generate another executable that prints 69. So that's kind of cool, right? So that would be the process of actually building the stack.sl compiler. So we need some kind of bootstrapping process where if you don't have the executable, you just run this these parts right here, right? And this thing generates you the stack compiler, let's say. And now after we have the stack compiler, we can just use stack for everything else. So that would be the idea. So let's try to solve the problem that I mentioned, because that could be quite interesting. And yeah, you can see it looks really ugly with all of these, but imagine that in the future we'll remove all of them because they're gonna be done by the compiler. So that's gonna be the plan. So if we're gonna have time for today, I think I'm gonna do just that. Otherwise, I'm just gonna do that on my own because it's quite straightforward, adding this stuff into the C compiler. But you have to be careful because if you add more stuff to the C compiler, it's gonna be harder to self-host the language, right? So each feature that you add, you have to also implement. So it's like I don't think that's a saying, but it's like a two-sided something. I forget. So yeah. Anyway, let's see. So if we go to the stack.ast expression, and the other thing that sucks about the language is we don't have an LSP. So yeah, but I kind of like programming this way because it feels like I'm doing the, you know, programming in Notepad++, like in my first ever coding experience, or I guess, let's be real, my first coding experience was in Notepad, not even Notepad++, so that's yeah, on another level. So as I was saying, right, so how can we simulate this stuff without unions and enums? So I guess the easiest question is, how would we do this in C if we didn't have unions or enums? So enums, pretty easy to figure out. We would just use define stack as the expression number, right? 1, 2, 3, and so on. So we would just use constants. So that makes sense. We can do the same thing here. So I would say, what was the, I would just say constant stack.ast number 0. And then let's take stack.ast expression name, right? This one is 0, 1, 2. I'm just gonna keep the same order. This one is 3. So that's how we build enums without enums. It's a poor man's way of doing enums. Okay, but how about unions? Because I mean, unions are you know, like the sum types from Haskell and all of those cool languages. Well, if we didn't have unions, what I would do is just have a void pointer for the union, right? And then based on the expression kind, I would know what this union type should be. So it should be a stack.ast node, it should be a stack.ast condition, and so on, right? So I would know which one to cast the type to, and also what to interpret the value as. So let's just do that, right? So how would that look here? Well, for stack.ast expression, we should just say pointer expression, right? So we have a pointer to something, and yeah, that's basically it. That's how we would simulate the same thing in C. So that's how we are gonna do it in stack as well. Now the only thing is that once we run the compiler again, so I'm just gonna run the type checking on stack.sl because I really thought it's gonna be enough to break. But I guess it's not gonna be enough to break it, so that's quite fun. Right, and the reason is this code is not generated by the compiler, right? It's generated by us, so if we make mistakes, it sucks. So I should just change this thing to pointer, and now it should fail really badly, right? So it's gonna complain about this stuff, so it's gonna complain about a lot of things. So first of all, we have the size of an expression. This is gonna be a constant generated automatically by the compiler, and it's gonna be the size of all of the fields added up together. So in this case, it's gonna be a pointer size of, so 8 basically. Then we are gonna have some constants for the offsets. So the offsets are gonna be named like this: stack.st expression dot field dot offset. And the offsets are just gonna be where in memory the field starts with respect to the structure. So in this case, it starts at the beginning of the structure, the expression, and it takes up 8 bytes. So let's go next. Here we have the init function for the expression, which will also be generated by the compiler in the future, hopefully. So the first step is to allocate memory for the structure. So we need to allocate this much. In this case, it's going to be 8 bytes. Then we have to implement the setting of a value. So you just have to trust me that this is going to work. And what you have to change is here you have to put the offset of the field, and this is going to be the last field of the argument. So in this case, it's the expression field, right? We offset the data pointer. We then have to generate a reference to our field value. So it's going to be, since you have a pointer here, we need to generate a reference to the pointer. So now, right now, it's like having a void pointer in C, right? We reference that thing here. Then we need to take the size of that field. So since it's a pointer, we have to do size of, and then we memcopy that thing into our structure. So you can see here that the reason why we needed to reference it is because we are going to use memcopy, and memcopy takes a reference to a value. And I know we have a pointer here, but the pointer itself is the value, right? So the pointer itself is the value that we want to copy. It's not the thing that's inside the pointer, but it's the pointer itself that we want to keep in our data structure, right? Because the thing is that each of these can have a different size of, so we don't know what size of to allocate here, right? And that's why we have to use a pointer, because in this maybe stack.st node is smaller than stack.st condition. Union kind of takes care of that by allocating the maximum size, but I mean, this is just easier to use a reference to that. Anyway, so that's everything here. We just push that and we have it, right? So then we just dereference the pointer, so the original memory. We dereference it and say, okay, that's this type, stack.st expression. So we just unbox that pointer and say, okay, the stuff that's inside that pointer is a stack.st expression. So that's pretty nice, I would say. Okay, so now the program should still fail because you know, we changed this value. So it's going to complain that the 69 that we had before is so I forgot something, I guess. Okay, yeah, and also we need to change this thing, so the getter. And the getter as well is gonna be data type dot field name. It's gonna return the field type, so pointer, and we have to do something like we generate a reference to our data type. We then add the offset of the field, so expression.offset. We use pointer plus for that. Pointer plus takes a pointer, a number, and it offsets that pointer. And then what we have to do is to unbox the new pointer as whatever we have there. So because we have a pointer there, we dereference a pointer. So yeah, I mean it's probably kind of like mind-boggling for someone to just think about pointers, but yeah, I don't know how you can think about pointers as literally just boxes. So if you have a pointer to a pointer, you have a box in a box. But I mean, I like to think about pointers as integers, to be honest. So if you think about them as just numbers, it becomes a lot more easier. Or at least for me, that's how it works. If I just think about them as numbers, it's so much nicer. So on line 164, probably here we emit something. Right. So this part right here. Whoa. Let's go back for a second. So the other thing, so we just added a pointer here, right? The other thing we should add is an integer for the kind, and you know, almost forgot about it, but we need to add an integer for the kind. So here we are gonna get an integer and a pointer, right? And you can see how easy it is to add another field because we just copy paste. We just we need to add the offset first, that's for sure. And the offset for the kind is gonna be basically the stack.st expression.export.offset, so the offset of the previous field plus the size of the previous field. So, well, I mean, I put them in the reverse order, so I should say here 0, here is gonna be int.size of plus, and now the expression has an offset, so it's gonna be the offset of the kind plus the size of the previous field. So if you think about it, the offset of expression is gonna be size of int, right? But I think it's better to explicitly state that it's offset of the previous plus size of the previous, because this is copy pastable. If we add another field, it's going to be size of this plus offset, so pretty nice. And now we can go back here. So oh yeah, and the other thing about the constructor, you have to realize that these are in the reverse order. So you first set the pointer, so the last field, then you set the second to last field and the third to last, and so on until the first one. So you have to set them in the reverse order because stack is, you know, it's LIFO, right? Last in, first out. Okay, so we do the same thing. We add the offset of the kind, right? Now the type of the kind is integer, so we reference an integer. We take the size of the integer and we run memcopy. So that's everything you need to do to add another field. And that's why I think it should be extremely easy to automate this thing into the preprocessor, because you just have to modify this thing into the field name, this thing into the field type, and this thing into the field type. And this is just like an algorithm, so it should be quite easy to run this stuff in the preprocessor. And then the same thing happens for the field getters. So here we add a field getter for kind, which is going to return an integer, and you just have to still reference the data structure add the offset of the field and dereference that thing with the actual type, so integer. Nice. So let's continue with type checking. So we want to go to 174 now, right? And here it's going to complain that, well, you are trying to access something that doesn't exist anymore because we no longer have number. We have numbers or names. So what we are going to do, we have to dupe our expression. So we are going to have something expression and expression. Then we are going to stack as the expression kind. So we are going to generate our kind. So we have some stuff, the expression and the kind. All right, so now we should dupe the kind, and we need to check whether the kind is stack expression number. If it's equal, then we have the assembler and the expression on the stack, right? If it's not equal, we can check whether it's equal to stack as the expression name. And at this stage we also have this stuff, and if it's not, we can just panic because it's unreachable, but we don't have that yet. So on the else case, and then we have 50. So here we need to emit, so let's do a to do emit name, and here we need to do emit number, right? So that's basically the idea here. So here we have assembler expression kind, right? So let's just have a couple of functions. Emit expression number is gonna take in, it's actually gonna take in I think it's gonna take in stack st node directly, and name is gonna work the same way. It's gonna take in an st node for the name, but that means I have to get the pointer. So I'm gonna do something like stack st expression, then already forgot. It's expression. So this is gonna give us assembler and pointer, and we want dereference this pointer as a stack st node. So luckily enough, we don't have any new types, so we just dereference it as a node, and then we can just call the emit function for a number, right? And this thing is gonna consume everything, so at the end we are gonna have empty. Oh, and here it's gonna be panic and pop2, just to make the type checker happy. Okay, so to emit the name, we just do the same thing, and as I said, it's pretty lucky that we have the same same type here, but yeah, it just happens that we have the same type. So yeah, okay, and we have to just move all of this into emit number, and yeah, we don't have constants yet, so we just push the number straight into the stack. But what are we gonna do for emitting a name? To do look in main.c, right? So that's what we need to do to figure out what to do here. So let's take a look at main.c, and let's see where we do that. So we assembler emit a program, we then go to emit function expression, and then we have expression name. So it's exactly the same. Okay. So even here we have different like constants and functions, but whatever. So we just have to emit a call to a function. Right, and let me just copy paste this stuff and you'll see why in a second. So I have this function, stack assembler func name, which does exactly all of this part from the C code. So it generates a new, but I want to find this because it's gonna be easier to copy paste that. So yeah, it basically generates the name of the function based on the function name and the internal counter of functions from the stack assembler. So yeah, it's like we don't even need to call this stuff anymore. We just have to make sure that we put here the right function name. So stack.st node, if we take a look, it has a string value, so we just have to access that string value. So let's take first we need to swap anyways. So yeah, it's like after we swap we have assembler first. So here I guess we want to have name assembler. Maybe before that I even want to do something like stack.st node.value, which is gonna generate assembly and then actual string. Right, so what would happen maybe if we do a rot here? We are gonna have the assembler string, then we call this function with these two arguments. So if we take a look at the definition of this function, it takes in stack assembler and string and returns a string. So after this stuff we are gonna have assembler and string, we concat with call, and then we call to emit. So yeah, this stuff looks good to me. So this should in fact give us the function name if we have a function name. So let's rerun the compiler with type checking. So it's gonna complain, it's gonna say that we don't have a stack expression number on 175. Well, I mean what? Stack.st expression dot, but here is stack.st node.value. Not sure why I had that. 187. So on 187, excuse me, what? So we had a string, then we swapped and we have string and stack assembler. Oh, I only need to call dup once. Nice. Pop2 on 189. I guess that's true, but I want to, so you can think of this as having a string and the assembler, and then string assembler. So I would maybe even do a dupe 2 here just to still keep everything. Well, maybe that's not true. Maybe I should have done a dupe. So we get the name. Wait. We get assembler name string. Assembler name string. So I have to rot. Then we can dupe. I see if you dupe there, you have NSAA. I was just trying to get to this stuff. So maybe here after we generate the value, I can just put all of this. So it makes things a bit more easy. So here we just generate the call string directly. Right, so we have dupe, so we have assembler name, then we have assembler name value, assembler name value. Shit. Okay, let's just start over. So we have dupe, so we have assembler name, then we take the value from the name. So we have name, so we have assembler name and the value. Then we have to we do something like rot dupe rot, but let's do just that, name value assembler. So if I do another rot, I'm gonna bring value first. Right, so now we can call to this stuff. So we are gonna remove these two and generate a function name. Then we are gonna put call swap string concat. So we are gonna have name, assembler, and call. Right. So then I would just probably do a swap. So we have a name, call, assembler. Then I dupe rot emit. So after dupe we have assembler twice. I put call first, and then we are gonna be left with name and assembler. So I think that's fine. Still kind of don't like it, but it is what it is. Yeah, whatever. Let's just live with that. $195. So at this point, it says that this has non-matching args. It expected a stack.st expression but got integer. So that's interesting. It's because we have a dupe here. We still have the kind afterwards. So we first need to pop. Forget about that. So here we need to pop 3 times. Okay, nice. And now we just go to the main function probably, and it's gonna complain that, well, we don't provide the right inputs to the init function. So 284. So here stack_st expression init, it expects int and pointer, but it got whatever, right? So what do we need to do is to provide the kind, so stack_st expression number, for instance, right? Expression number. Then we need to put 69 and stack_st node init, and this is actually the expression that represents a number. So if we run this, wait, that's interesting. So stack_st expression expected int pointer, but we got int and ast node. So the last thing we need to do is convert the stack_st node into a reference. So now it's a pointer, right? It's that pointer that I talked about, so that we have a generic type. So now it compiled. Let's see what happens if we actually run this thing and we still get the 69 that we had before. So I guess question is, how can we actually append multiple expressions? How can we actually append multiple expressions? So here we have node and expression. Let's just say we are going to put another expression, so like, I don't know, 42, 27, and then we have stack_st expression name, and the name is going to be plus. So we have 42, 42, 27, oopsie doopsie, 42, 27, and plus, right? And then we create an array, and that's interesting. Stack_st function, stack_st function here, it has an array of expressions, right? So that I don't think it changes. So we create an array of, so here we have the expression, let's just say, right? So the algorithm of pushing stuff, let's just do the algorithm. So it's gonna be dup, we bring it forward, we make the expression into a pointer, we call to append, and then we do this panic check. So this should in fact leave us with, for instance, oh, but it's the reverse order, so I should put them like that. So it's gonna be, yeah, I forgot about that. So right, it's gonna be the reverse order. So it's gonna add 27, so we are left with plus and 42. Then if we call this thing again, we are gonna be left with plus, and again we are gonna be left with just that. So then we can call to function init. It creates a function from a node and an array of expressions. Then we can just do something similar here. So here we have function and array of functions. then we call to dup, we rotate stack.ast function address, append, and do the panic stuff, right? So here we just push function into the array, and then we create an AST program. And yeah, that's basically what we need. So let's try to compile this stuff. And interestingly enough, we still get 69, right? So if we take a look at the main function, you can see that, I mean, it looks really weird, but you can see that const string 42. I mean, this is the compiler code, right? So you can see how it builds up all of these instructions, but the actual code of the executable is going to be like program.assembly, and in program.assembly you can see it prints every assembly, and then in the main, oh, I didn't add comments. I was hoping I had the comments for main function, but I don't. So it's function 0. I guess function 0 is the main function. So you can see it pushes 27, it pushes 42, and then it calls to function 6. And function 6 is plus. So that's kind of cool if you would ask me. So we are able to, well, we are just able to build an AST and compile that AST to assembly. So I think that's pretty nice. Right, we have assembler emit AST, then we have emit function, and so on. So it was just one small thing I didn't like, that it was unaligned. Oh, I have anyway. So if we check prog.assembly, yeah, I really like how main is function 0, but I guess that's just I don't know why that happens, but I'd say it's pretty nice, right? So we are able to have different kinds of expressions, and yeah, we can just compile some AST stuff, which is a good progress. So, you know, next time we'll probably try to get if statements into the mix. Like we can just change this thing to a minus, and it's probably gonna work, right? We get, I mean, it's negative because it's 27 minus 42, but with the point, we can just do any computation now. We just need to build the AST. Ideally, I'm not sure if I want to add more expressions or if I want to go to the next layer and add tokens and start working on building the AST from a list of tokens. I think that's gonna be cool as well. So, you know, probably I'm gonna add more nodes here or something, and then we can go to building the AST from a list of tokens, because imagine that if we had a list of tokens, it would be much much easier to do everything, would look less cluttered. So yeah, I think that's pretty good for today. I think hopefully it was interesting to see how we can do these kinds of data structures. So as I said, why not just try to implement these things automatically in the compiler now at this point, because I think we can in the C compiler. So let's try to do that. Right. So in my opinion, this should be a preprocessor step. So let me just have something like feature added expression pointer. So I'd say this should be a preprocessor step. All right. That's what it feels like. So let's just go to main.c and let's go to the preprocessor run. So preprocessor is gonna do a for loop over the imports. Right. But maybe it's a lot more complicated because we have to build a dependency graph and run preprocessor on each file that we parse. So let's just say that I'm gonna run the preprocessor. So what is exactly the preprocessor? Oh, so it's nothing relevant. So I could, because here at the end, we have prog new, but prog new is completely new. Let's make things a bit simpler. And if stuff fails, it fails, right? So it's like a it is what it is moment. So let's have here a stack ast program, and this is gonna be the import or program import. It's gonna be the imported program. Let's initialize it. All right, let's initialize our imported program. So we get the stack home, whatever. We read from the lib folder. Yeah, we read the file, we append the buffers for memory management, we create a new lexer, makes sense. We initialize the parser, do some stuff, and then what if we prog import here? Right, and then we can do something like append many at the end here, and we are going to say we append to constants from prog import, from datas import, and from functions imports. And same here. Shit. We just do that. Is this gonna work? So I'm just gonna use main examples rule 110 as the test case. It looks like it still works. We don't have any errors. What I'm curious is actually running also val grind on this. So it looks like we need to free free the prog import. So I have to do something like, wait. Why do I have to do this? Huh, no idea. I guess also consts, but that's, I guess I have to free them here for prog import. Free the arrays. Alright, whatever. So that's what I would do for prog import. Interesting. Well, maybe actually that's dumb. So let's just say that no, I won't do this. I will just generate the entire AST, right? So let's just remove the changes. So here I go over the imports. I import the file, so it's cuffed for now. We cannot have multiple programs. We just parse into a single program, right? And here at the end, what we need to do is go over the datas and generate cons and getters, or I guess init and getters. And that's what we have to do, because right now we have all of the programs, like all of the datas from all the imported libraries. So it should be like, yeah, we have all of them. That's nice. So I'm gonna do a for unsigned int I is equal to 0. I should be less than prog, and I guess prog is the new prog, so I can just say prog dot datas dot count I plus plus, and here we get the data. So I might want a function static void stack preprocessor generate data init. Let's just call it that way. So let's say we have a stack preprocessor, just to have it, stack ast prog, because I need the reference to prog, right? I need the reference to prog, but I also need the stack ast data, or maybe I can just give it int I, like which one, but I like more to just give it the data. It makes it more. So maybe this one should actually be the second argument. So it's like this is gonna be the output. So it's like the forbidden. It's fine. It's the forbidden Rust logic. You cannot have mutable and immutable references to prog, right? That would be forbidden. But in C you can, and no one can stop me. I mean, a segfault will stop me, but you get the point. Unreachable. Yes, dynamic array get. So we want to get the data, and now let's do stack preprocessor generate data init. So I don't think we're gonna use the preprocessor there, but I would say it's good practice to keep it. So Yeah, probably it's not gonna fail. This function, I don't think it's gonna fail. Like, I don't see how, unless you like it's up to the type checker to fail missing functions and stuff like that. So this is just gonna imagine that you have all of the things. It's just a code generator tool, right? So let's go straight into the part, right? So what do we need to do? Well, we need to stack ast function. We need to create a function, and let's call it init. So this function is gonna have a name. So this name should be a stack. Do I have stack ast node? I have. It has a value parser position. That's interesting. Right, that's really interesting. Oh, I know. Yeah, it's gonna be cool, right? So I just need to see the stack ast node, so it has these fields. I just need them. So let's put some comments in here. So these are the fields of a stack ast node, right? So the value is going to be a string slice, and the string slice should be, oh, actually that sucks, but let's build the name. Let's build the name. So the name is going to be generated like this. The name is going to be, right, we need the SB. The SB, and we are going to say dot init. And here we have data. I think it's data.name. I'm not sure, I don't remember. Data name, yeah, nice. So we generate the function name right now, right? So it's gonna be data.init, and this is gonna be init name, right? And init name it should be a string slice, which we can say it's 0. But string builder build, oh, I'm not gonna do string builder build, what the fuck? I'm gonna do ds string builder to slice sb. I'm just gonna call it name. Right, that's nice. So stack ast node. This is gonna lose memory though. I should add something like int allocked, right? And when you initialize, for example, dot allocked is gonna be equal to 0, or it's like boolean, right? Allocked is usually boolean in my code. Yeah, nice. So it's gonna be false. It's not allocked, but here if okay. I have to do something like this, I guess. So if the node is allocked and the value str is not null, then we have to ds free value allocator node value str. And so we have to do this extra step. And yeah, I'm not gonna break the stackst node thingy, but I'm gonna do stackst node A or something, and this is gonna be true. So now I can just say it's allocked, so we can pass here the name. Parser is gonna be data parser, or data name parser, right? And then we have the S, which is the position. I think it's the position, so position should be data name position. I'm gonna put it as data name position, I think. Stackst function doesn't have a need, so we need now the arguments. So dynamic array, yes, dynamic array args. Let's just say ds dynamic array init. So it's interesting. Args is stackst node. That's perfect. So we initialize the args with size of stackst node. Cannot fail. So that's what we do here, and then we expect ds dynamic array. Let's append to our args, and here we need to append a stackst node. Am I right? Stackst node, and actually we need to do a for loop, but assigned int I should be less than data fields count I++. So we need to add each fields type as the arguments. So you might say, okay, but look at stdlib and look at array has all of these fields, but its constructor has only int. How are we gonna fix that? Well, the array constructor is actually gonna construct all of the fields, but we're gonna have a wrapper around that constructor that takes in only an integer for our convenience, right? So that's gonna be the idea. So here we do unreachable ds dynamic array get, and we pass the data fields index I, and here we need the item, or I guess the field or something. So the fields is what is a stackst data field. Nice. So I'm gonna call it item, why not? And what does a field have? It has a type and a name. So I said we care about item.type.value, item.type.parser, and item.type.position. So ds error out of memory. So in case we get errors, I think I'm gonna print the error at the field type or something. I don't know. It kind of makes sense to do it that way, but that's how we do arguments. Perfect. Let's also do, let's do the return. So the return is gonna be much easier. It's just so rets, we initialize the rets. It's also stackst node. I don't even need to check, I already know that. And it's gonna be the data name value, data name parser, and data name position. So that's how we initialize our arguments and return values. So let's put here args is args and reds is reds. And we just initialized our function, and yeah, we need to initialize the body. As well, which is also a dynamic array. And now I think it's gonna be more interesting. So it's also stack st nodes. It's gonna be more interesting. So if we check stdlib, and let's look at string. Maybe string is the best one. So we need to call this size of function. We need to call this string.size of function and pointer alloc. And it's gonna be so interesting. So let's reuse our string builder because I'm too lazy to do another one. So it's gonna be, as I said, string.size of. Right, I don't like that we have to use it. Define stack process stack data size of, and it's gonna be size of. What the fuck am I doing? Stack data size of. So I think I don't like. Yeah, I don't know what I was thinking here. It's not gonna work. So it's gonna be like this. Stack data size of. We convert it to a slice. But yeah, see here yeah. It's interesting. I don't free this thing. I thought I have to free the array. Well, I mean, I'll see. Yeah. Let's not worry about that stuff. So this should be like the function name. Actually, let's do it like this. I mean, the SB can be reused, doesn't make sense to keep it there, but let's have this thing as a node, right? So stack st node is this thing gonna work? We'll see. If I have to, maybe, I don't know. I feel like it should. I don't know why wouldn't it work? Right, because here we make a copy of it, so we just move the copy there. Here we write into it, but it's already copied, so it shouldn't matter. So this should be the name of stdlib of the string.size of. So we need to add this to the body. So let's take this and let's append dynamic array. Here we are gonna append the name, and I'm gonna keep data name position, and yeah, but here we need to put body. All right, so I think that's the first step. I'd like to see if it actually does something, so let's go ahead, and we have generate data init, and also consts, offset and size of, right? We need to generate those as well. So let's run make, and let's do lib/stdlib. Let's run the p, and let's run now the preprocessor. So preprocessor, we should see something like function string dot init. So we have our original one. I don't see it. Oh, because I'm not adding it, right? I'm not adding it to the program. So I should say vsexpect dynamic array append prog funcs, and then we just pass the init function stack ds error out of memory. So we should add it that way. Okay, so let's see. Oh, it's supported. I mean, who didn't see this one coming? Oh, so it's right at the pointer, but pointer cannot have an init function though. So I have to skip this one for the, I mean, you know, it shouldn't segfault even for pointer init, because yeah, it wouldn't make sense. But I'm curious where it was allocated, because it just died. It just died. So maybe I made a mistake somewhere around here. So can I do stuff like printf percentage point star s node dot value dot len node dot value dot str, and let's take a look if we find the here message. Oh, I mean, those are generated nice. That's nice. But again, I shouldn't do that for the I mean, even here I should say it's allocated, but you get the idea. So this one is name. Let's print the name. Maybe I did something wrong in one of these, although I'm not sure. It looks good to me, but so these are the original ones, and this is the new one. So it looks good, but why do I get an error? Let's try. Let's remake, and let's run leak check full. Leak check equals full. So maybe I can see something where we broke something. I don't know. So this address is not malloced. So it happens somewhere at line 1119 when I try to stack the expression dump. But see how it died here? And it doesn't show me the line number? That's so weird. But I mean, I know where it died, right? It died, it tries to print an expression of type name, right? It's stack expression name. Oh, you know what? The body is incorrect, right? So the body, I mean, it's fine. I said, oh, body, it's gonna be just no, it's an expression. Oops. So here it should be expression. And here we need to append an expression. So do I have stack st expression? Expression name, nice. So I do have that. Perfect. So let's generate the expression and let's append that. Right, so like this. So that was one of the issues. Do we have more? I mean, maybe. It looks like one block. It's not. Okay. So let's search for. Oh, we have array init. Nice, right? We just call size of. It's like the first step, but we are doing something. But as I said, function pointer init shouldn't really be a function because external functions don't have anything interesting to them. I'm also curious where I did lose this stuff. So 1023. I forgot to free the consts. Maybe. Stack st free. No, I freed them. Huh. Anyway, let's continue. I'm like completely lost. I have no idea why this thing is not freed. But let's not care about it. Let's just go ahead and say here that if data is external, then we continue. We skip this process. So we just managed to add the first step. We now need to add pointer alloc. I mean, it's interesting if I do string builder to slice. Oh yeah, I don't have, yeah, that's so nice. I don't even have to free the string builder. Right. Yeah, because I convert it. Okay. So for example, here, I need to do stack function pointer alloc. But these ones should come somewhere higher up. I guess I'm just gonna put them here. So I just put now the alloc function. So if we rerun this and we check, we also put pointer alloc. Nice. std lib. So now we have this thing to append. So it's gonna be, some things are gonna be easy and just copy paste, but some of them are gonna be more interesting. So now we have to do a for loop over the fields again. So we need another for loop over the fields. We get the field, right? And now we need to do some stuff. So stack func dup. Sadly, I don't think I can. Oh, actually, you know what? These are not alloced because they are just string constants. So why do you complain? The fuck? Oh, it wants. Oh, I mean, this string slice, right? I have to call string slice at least on it, but it's still better than doing all of that, in my opinion, because we don't need to. Let's put a comment. So here is gonna be calling just dup. But I mean, it's, the code is really long, sadly, but let's just go through it. So this one is interesting. We don't have rot prime. We don't have rot prime. But I can just add it, rot p. Right, because these are rot prime. Now it's gonna be an interesting one, this one. But let's continue with function ptr offset. Let's do, oh shit, swap. We have pointer end. Okay, then let's just do it here. So we need this stuff, and let's do string.str.offset. So what we need here is the structure name, a dot, then the field name, a dot, and offset. So we need the data name, we then need the field dot, or I guess it's called item dot name dot value dot len, item dot name dot value dot str, and then we need the word offset. Then we generate that and we append. I guess I could just append the item name. I'm just gonna put data name everywhere. Yeah, I don't know. Let's just put the data name. It's like they are not really gonna fail because I don't see how it can fail, but who knows? Who the fuck knows? I mean, it can happen. So next up, we need to put pointer end and pointer size of. So here it's gonna be the data, like the field type. So field type value, right? That's the thing we need to put to generate this thing. And here is going to be the data type dot size of. So that's going to be the thing we need to put next. So data type size of, and here it's extra. So that's the next thing, pointer size of. Pointer size of. Then we need to call pointer memcopy, which is a classic function. So we just do function pointer. I mean, we don't really have pointer memcopy, but stack func pointer memcopy. Let's just define it. Stack function pointer memcopy. It's like a function from standard library, but well, this means you need standard library to be able to have data structures. Yeah, I mean, whatever, right? You kind of need them. Anyway, so that's how we insert a field, right? We do this thing for each field, and then we have to call this function at the bottom. So we need to call the reference on the data type. So let's just copy all of this and say something like string star, and we're gonna do data, this is data name, and that's it. Right, so now if we remake this thing and we try again, we're gonna see that we just built the init. Right, and as I said, the init for array, it takes in all the arguments, but we want a special init that's gonna be easier to work with. So let's go to stdlib. That's the first thing I'm gonna do, and I'm gonna search for init functions. So, oh, guess what? Byte init is gonna be interesting. I mean, byte init is not even a type, so it's safe. Yeah. So string init is gonna go away, right? Because we just implemented array init. Let's make array init dot with sz or something, right? So we are gonna rename this thing. We'll keep all of this, and instead of like this stuff was extracted into array.init, right? So that's the only thing we need to remove. So now if we try to run this one, exactly, we have to change everywhere from array.init into array init with sc. So let's go to rule 110 and search for array.init, right? And let's replace it with array.init with sz. String len size of. Wait, what? String len size of. String dot len. Oh, I was smoking something there. So I guess when we are doing fuck, so here it should be no, that's fine. String len size of, right? It should be a function, string len size of. No. Oh, I have to say offset. Item type size of, but here it should be offset. All right, so we have the size of for types and offset for names. What am I doing? Stack data offset is offset. Okay, so that's how it should be. All right, and if we run this one, int end has non-matching args. So did I put them the other way around? Function int end 195. What the fuck am I doing? std lib 95. Hmm. What? I'm wondering which one broke, because we have it at 360 and 195. So how did I break it? Let's do minus p and let's see again. So I want to see function string init, because string init is going to be easier to work with. So let's go and have string init here, right? So we do have string size of do prot prime string len. Oh, I have to go counterclockwise. Well, I mean, from, as I said, we need to go in the reverse order, right? So I is less or equal than 0, and I minus minus, let's not forget that, that's important. So yeah, we have to go the other way around. Shit, what? 1274. That's funny. I cannot use unsigned int. I mean, it is what it is. And funnily enough, it still works. That's pretty awesome, not gonna lie. So, I mean, yeah. Let's just make sure it was saved. Okay, so it still works. Nice, perfect. So next step, honestly, would be to add these constants. Where are the constants? So len offset and size of, for example. So let's go ahead, and these things are going to be added only for non-external data types, because external data types doesn't really make sense, right? Because we don't know what size they have. So let's go ahead, copy this one, generate data init. Let's have another function, stack preprocessor, generate consts. Preprocessor data and program. Right, so we'll have something like static void. All right, and I mean vi yoink, vi point. I don't know what p stands for in paste and yank, but you get the point. So let's get these constants. So first of all, we'll have obviously we'll need these two data structures as usual, and we need to generate a constant this time. So we'll need to generate a constant, and the constant is going to be, I guess, wait, do I really, is there really a type const? Yeah, it is. So name and expressions. Name and expers. Let's call it expers. So this is gonna be size of, but I cannot call it size of because size of is a thing. So I'm gonna say it's size of. Okay, anyway. Obviously the name of the thing, size of, right? But yeah, we have the stack data size of, so we have that. We already know. So it's gonna be data name dot size of, and this is gonna be our node, right? Right, that's nice. So the next step is to have a for loop similar to this one, right? And we are gonna call this one expressions, and it's gonna be stack as the expression. We go through the fields, but not really. We are gonna do something interesting first. So if data fields, I don't know how you can have a count of 0. So if it's greater than 0, we create an item, we get the first one, and we append it to expressions. We create a node, but we need to create an expression though. We need to create an expression. So let's say expressions, and the expression is going to be a number. Stack st. No, it's going to be a name. It's going to be a name. Stack st node. Shit. And it's size of each type. Okay, so let's actually build that thing. So we initialize, wait a second, we have to do something like this better. It's gonna be easier. So we have to initialize the SB. We have to say it's gonna be data type dot size of, and it's gonna be the item type size of, right? That's true, and that's what we need to append to expressions, right? So we get the field, right? but we also have to do some stuff here. We have to do the same thing. We get the field. Well, actually, it's going to be easier if I just do it the original way to do it. So we start from 0 up to count. We what are we gonna do if count is 0? That's gonna suck really bad. Am I right? Yeah, anyway, so so we have something like this. We go from I to count and we add this size of expressions, right? And then we need to do like it's an edge case. If data fields dot count is greater than 0, we can do the following for loop of adding all the pluses. And the reason why we need to check for greater than 0 is because we are going to do a -1, right? And here we won't need the string builder because the name of the function is stack function plus, and it's not allocated. But here I need to say string slice. So I need to add a plus function at the end for this thing, right? And then after we do that, I can just add a constant. So in the consts, I can put size of, and that's how we do the size of constant. And now let's do the length offset ones because they are kind of similar in the amount of how annoying they are. I guess I'm gonna do them here as well. So let's just start. But this one is gonna be a for loop over the data fields. A for loop over the data fields. I mean, the first one is kind of special because it's only 0, but that's also true. So I'm gonna start at 1 then. And let's do the first one in a special case. So we are gonna take this stuff. We can just reuse node. And the name of that function is gonna be string length offset. So it's gonna be, okay, we need to get the first item. We need to get the first item. So it's gonna be fields 0 item. Again, this one is like if the number of fields is greater than 0, so this kind of sucks, but let's nest this bad boy. Okay, so we get the first item, right? And we are gonna call this bitch string length offset. So it's gonna be data name, then dot data field, and then offset. So here is gonna be field name value. Well, it's field, it's item. Always made this mistake. Field name value len item name value str. So that's gonna give us this offset, and this is gonna be the name of the function. Right, so we need to create this kind of size of structure. So this is item offset. We put a node, and as expressions, we need to initialize an expression, or I guess the array of expressions. Let's just say that we initialize with stack expression, and we only have one expression, and that expression is gonna be a 0. So I'm gonna say here that I want to build an expression number, and I have to say only the node. So stack st node, and the number is 0. This one looks good. Oh, so here it's ds string slice with 0 or something. Anyway, so that's the expressions. So this is going to give us item offset, and we need to append it. And now is the for loop, where we need to create a new one. We need to create a new constant, and this one is going to be called string field offset, but let's just take the item, and this time the item is going to be the ith1, so that's good. And here we have the new name, right? The new name, and we need also previous. So that's why I start from index 1. So we need previous now. Item previous or something, I-1, and here it's item previous. Well, it's like this is the edge case for I0, but it also works like this. So we take the previous item. We need to generate this string len offset. So let's do that. And for that one, we need this. And we need to initialize our expressions as well. So we need to have this array. Let's take this one a bit lower. So we have a new expressions array, obviously, and we have to say string dot field dot offset. So it's going to be data name value len, data name value str, and then we have item name and its offset, right? So that's that, and we add the expression here in expressions, right? And the last one is actually the type offset, type size of, sorry, which is exactly here. And then we need a plus. So the plus, we can steal it from here, and then we need just a plus. So we can just add that plus, and obviously this thingy as well, right? So I mean, I would honestly just consider combining these for loops together, because it might make things a bit more easy. So for example, imagine that we take this for loop, and put it here. Start from 0 and have something like, okay, so this is good, but then we have previous, which should happen only if I is equal to 0, we have something, and else we do this stuff, right? So that's the difference. And if I is equal to 0, then we just need to call to this thing here. We just need to append a 0. And then we have the exact same code, I would say. So I think that's gonna make things a bit more clean. It's a bit more easy to read, even though it's a if else in a while in a for loop. I don't really care. It is what it is. So let's go to std_lib, and we can just remove all of this string size of, string length, and the array ones. All right, we just removed all of those. Oh shit. String size of string that's off. Are you serious? Let's do -p. Let's see, because that's your opinion, I would say. Wait, what? Double free. All right. I mean, but I mean, I guess you get a point at this stage of what I'm trying to get, right? Probably I messed something up in one of these. So let's just comment this one out, for instance, and let's just say maybe I made a mistake in that code, right? And yeah, oh yeah, because I said it should be item offset, obviously. Okay, maybe that was a mistake actually. And I guess it was. So question is, where are the consts? That's what I want to see. And there are so many. Oh, there are the consts. Nice. So you can see that the consts are actually here. They exist. And they are not really correct. Oh, shit. So here, yeah, I should have used item previous instead of item. So here, for instance, it's item previous. Item previous, and here as well, where is it here? Size of the previous item, right? We want to get the offset based on the previous item. So it's going to be interesting how we are going to, because we already have experience with doing this stuff in Stack itself because of re-implementing the compiler, but yeah, it will be interesting to implement all of these in Stack too. Oh my god, so many functions, but now it looks better. I would say now it looks better. Yeah. So if I run this thing, it should still work. So I'd say I'm pretty happy. I'm just gonna do the getters and setters on my own because you already got the point. I think it's already super obvious to you what happens here. So yeah, that means we can just go to Stack and we'll be able to just remove all of this crap, right? Which is what I was hoping to achieve at some point, and apparently we just did. So that's really nice, right? So we can just have data structures at this point. We no longer need those things, right? So we just have data structures and it's much cleaner and we can just see what happens. But yeah, I have to just add those field getters, and you know, we made quite a lot of progress, so pretty happy with the results. So for next steps, I'm probably gonna add more expression kinds, right? And we'll see how we can maybe add more stuff here too, because you can see we add expressions. Maybe I can add on my own the other pointer types here, and then maybe we can start on like, instead of building the AST manually, maybe we can have a list of tokens and build the AST from a list of tokens. So yeah, that's the plan for next time. So I mean, you know, maybe it's gonna be tomorrow, maybe it depends on how long it takes for me to finish these small features. So see you in the next update.